Welcome back, guys. Having discussed the theory behind transfer learning, we now proceed to implement it into code. We will use the Cypher code from earlier. I've cloned a copy and renamed it to transfer learning, as most code cells from the Cypher code will remain relatively the same, as we will only change a few things. So if you lost your Cypher code, make sure to refer to the GitHub repository that I mentioned in the introductory part of this course, and once you do load your Cypher code, we'll get right to it. So first we will start by creating our model. In the previous sections, we created a class and defined each layer of the model with all the parameters and then began the training process. The more we increased the complexity of the model, the longer it took to train. Now using transfer learning, we can bypass the long training time and still use very complex architectures that yield reasonably high accuracy. Luckily for us, we're able to harness pre-trained models, restricting training to only a few layers, and utilize these sophisticated models to classify our own datasets. So we'll start by loading the model, but before doing so, from Torch Vision, right over here, we're going to import models, like so. And you know what, before continuing, I realized that I should probably run some installation cells, so I'm just going to do that and fast forward the video until it is complete. See you guys in a bit. Alright, back to it. This is the package that will allow us to import a pre-trained model into our collab notebook. The subpackage contains many different model architectures like AlexNet, VGG, ResNet, SqueezeNet, DenseNet, Inception, and so on, whatever you want. And as for the dataset that we will load onto this project, I have prepared an ants and bees dataset on GitHub that we will clone to get access to it. So on a new cell, right after device torch.device, I'm going to create a new cell over here, Alt, Enter, and we will use the git clone command, and the GitHub link can be accessed from the previous article. Make sure to copy it in order to access the dataset. Now this bees and ants dataset was created by us manually and was very simply done, as they are images straight from Google Image Search, which were then placed onto folders and then uploaded to GitHub. Really nothing to it. You can collect your own datasets pretty easily, but just work with ours for now. Now let's check and see what's inside. So from this cell, I'm actually going to create a new one, and we're going to write ls. We see that we have an ants and bees folder, some sample data, and some other data, which we're not going to concern ourselves with. But regardless, from ls, we create a new cell. And I want to see what's inside our ants and bees folder. Well, I already know. I want to show you what's inside our ants and bees folder. So if we write ls and specify the following path, ants and bees, we see what seems to be a training set and a validation data set. Let's check and see what's inside of our training set. So on a new cell, we're just going to write ls ants and bees and navigate to train. Alright, as you can see, we have an ants and bees folder. Let's navigate to our ants folder. ls ants and bees /train/ants. Alright, and it displays a list of all of our images. The model we're going to use for this dataset notably was trained on the ImageNet dataset, which I've mentioned consists of over 14 million images of all sorts of things. However, the images from the ImageNet dataset are 224 by 224, so we must make sure that the images within our own dataset are also resized, are transformed to be 224 by 224 to reflect the same size as the images that our neural network was trained on. They will be resized to 224 by 224 to remain compatible with the pre-trained models we are going to use. So, enough talking, simply enough, we just resize 224 to 224. And we must do the same thing for the transformations occurring on the validation dataset. Okay, we will leave the augmentation. Well, it would definitely be to our benefit to make use of augmentation techniques, since we are dealing with a very small dataset. And now actually, loading the images we just downloaded and storing them into training and validation dataset variables will require the use of image folder. We are not making use of Cypher 10 anymore, so we write training dataset is equal to datasets.image folder. And this will take in a path to which our images are located, which you can copy from one of the paths from earlier. Ants and bees / train. And we will copy it as a string value. Right over here. We do not need the ls command here, that wouldn't make much sense. And we do the same thing for the validation dataset. Ants and bees, except I remember the extra path here was val. Having specified the path to which we want to load our images, the validation and training images onto the appropriate variable, upon loading them we must apply the appropriate transformations. Transform for training will equal transform train, as it already is, and transform for validation will require validation transform. Okay. Now as for image, forgot to replace that with image folder. And as for image folder, it simply arranges the images based on the folder they are in. We specified the train directory, and in the train directory, remember, there's a reason why I put all these cells. We have two folders, ants and bees. We use image folder to automatically organize these images, assigning images in the ants folder to be in folder 0, class 0, and images in the bees folder to be in class 1. Essentially, the images will be pre-labeled such that all pictures of ants will belong to the first class and all pictures of bees to the second class, such that we will have the first class denote ants and we will have the second class denote bees. And now the validation dataset is split in much the same way, where the first class will contain all the ants images and the second class all the bees images. So now we have a training dataset containing images of ants and bees, all of which have been labeled into their appropriate class, and we have a validation dataset with images of ants and bees in much the same way labeled into their appropriate class. We can now observe the lengths of both our training and validation datasets by simply going on to a new cell and writing print length training dataset. Let's just copy it. And printing the length of the validation dataset. All right, printing the following. We have 244 training datasets, or training images within the dataset, and 153 validation images. Although the dataset is relatively small compared to other datasets that we worked with, you may think to yourself that this is not enough to fully train a network. Well, you may be right if we were using it to train a neural network from scratch. However, we are using a pre-trained network, so recall what we talked about in the theory portion. If you don't have enough training data to train your own network with, then you must rely on other models that have been trained on similar data sets. Our pre-trained model for this case has already gone through such vigorous training and is effective at feature extraction, and so we hope that this small data set is large enough for our pre-trained model to work with. Now before proceeding to grabbing our model, I'm going to reduce the batch size. Since our dataset is so small, and accordingly we access it in smaller batches. Now since our batch size is not 100 anymore, something needs to change. I've already addressed this earlier in the MNIST section, but once again you may have already noticed in here that to get the epoch accuracy, whether it's in validation or in training, we simply divided by the number of batches. I have done this intentionally since for each batch, we checked how many of the images are correct based on 100 images per batch. This automatically gave us a percentage, and then doing this for every batch and dividing by that number of batches would give us an average percentage. However, suppose for whatever reason you change your batch size to 90. In our case, we set it to 20, as our dataset is relatively small. By doing so, we would not obtain percentages anymore for our accuracy. We would get relatively odd numbers, which would be pretty hard to interpret. However, if you divide by the entire dataset, namely by writing trainingloader.dataset, what that will do is it will give you a probability that ranges from 0 to 1, as you're dividing the number of correct predictions by the total number of images. For consistency, we do the same thing for the loss, trainingloader.dataset. For teaching purposes, as I've mentioned before, I thought the idea of automatic percentages would be more intuitive to start with, but as we are changing the batch size, we must make the following adjustments. And doing the same thing for validation, dividing by length of validation loader.dataset, and once again here. All right, and having fixed this earlier problem, we now go back up and load the appropriate training and validation datasets into our data loaders by going down there. And it looks like we've already done so there's no need to change that. Another cell that we must change is that since we are dealing with only 2 classes, rather than the 10 classes from Sci-Fi 10, we specify them accordingly. Ant and B. Note that the order is important, as the ants are going to belong to class 0 and B's to class 1, so the list or the tuple we specify here must respect that order in order to get accurate results. All right, and now plotting the following. You know what? Let me just rerun everything from scratch. We may have missed some cells. We seem to have an error. Module pl.image has no attribute register extensions. What I'm going to do is right here, instantiate a new cell, and we're going to install Pillow version 4, since the current version seems to be causing some problems. Version 4, rerunning our cells. And once again, looking at this yourself, you can just see how difficult this classification task is. One would say these images are a little bit more ambiguous than the ones we dealt with in the last section. Some of these images are very dark, while others are very bright. Some are close up, while some are a bit zoomed out. On top of that, ants and bees don't look that different to begin with. So it will be interesting to see what kind of results we can obtain from this. We will first start on a new cell. We're going to delete the following. We're not going to build our network from scratch anymore. Well, at least not for this section. We will start by using the award-winning AlexNet model, which we can load using the previously mentioned subpackage models. Accessing AlexNet, models.alexnet, and we will set pre-trained is equal to true, and storing that in a variable called model. Simply enough, all we're doing is loading a pre-trained model from PyTorch, and we set pre-trained equal to true for the model to be loaded with all the weights obtained from the previous training process on ImageNet. Run the current cell, and on a new one, let's print the model and see what the architecture looks like. We do this by printing model, and it seems like we successfully loaded the model. It contains 5 convolutional layers and 3 fully connected layers, as we saw in the theory portion, such that ReLU is applied at the convolutional and fully connected layers, and dropout is applied before the first and second fully connected layers, which makes sense as fully connected layers generally imply the presence of a very large number of parameters. Now there are still issues to address before training the model in our own datasets. Recall from the theory portion, we must freeze the parameters inside the feature extraction part of our network, such that the convolutional layers will be unaffected by training. We are going to then use the feature extraction knowledge they have developed without tampering with it. We will keep the fully connected layers dynamic, as we want them to learn which features are important to classify for our specific dataset. So the parameters in the fully connected layer will change and adapt to our small dataset. And now freezing the parameters inside the feature extraction portion of our network is done by first creating a new cell, and we will write the following: for param in model.features.parameters. All right, this will loop through all the parameters in the feature extraction portion of our model, and then we set requires, or params, dot requires grad is equal to false, which will essentially freeze those layers, such that it leaves these parameters unaffected by the backpropagation process that normally updates these weights. They will not require the gradients. As mentioned by documentation, setting requires grad equal to false. This is a very useful technique when you want to freeze the part of your model and you know in advance that you're not going to use gradients with respect to these parameters. Now the second issue we must deal with is that the last fully connected layer of the classifier has an output of 1000. For our purposes, the output layer must only distinguish between 2 classes rather than 1000, whether something is an ant or a bee. To resolve this issue, we are indeed capable of slightly modifying our current model to add another layer of nodes, replacing the functionality of the old one, and make that the output layer instead. Since we only have 2 classes in our dataset, we must change the output of that last layer in the model to suit our purposes and only have an output of 2. To do so, on a new cell, what we're going to do is import torch.nn as an n, once again accessing the nn module. We define the number of inputs as n inputs, and what we set this equal to is dictated by the model summary we printed earlier. When we previously printed the model, we can see that it was constructed with a sequential module. A sequential module contains other modules, i.e. convolutional layers, fully connected layers, activations, dropout, etc., and applies them in sequence. This model has 2 sequential constructors, the first for features and the second for the classifier portion, which consists of the fully connected layers at the end. We don't want to touch the feature extractor. Recall we froze these parameters inside the feature extraction portion of our network, such that we're able to use feature extraction knowledge without tampering with it. Therefore, what we want to do is access the 6th element in the sequence of the classifier and retrieve the input features of that layer. So what we do is we set n inputs and we set it equal to model.classifier. Feel free to copy that right over here, and we will access the 6th element, this linear layer right here. And we want the input features, .inFeatures. Feel free to just copy that. And so we call the 6th element in the sequence of the classifier with the goal of retrieving the input features of that layer. Simple enough. Now, since these input features, these 4096 inputs, are what will be received and passed into the newly modified output layer, all of which are now accessible by this variable, what we need to do is pass these input features into a new last layer, not this one. Last layer. And recall that creating a fully connected layer of nodes can be done, well, has always been done in this course, with nn.linear, taking in the n inputs, and the number of classes we could simply hard code as 2, but suppose you wanted to change your dataset, let's make this code a bit more adaptive to be length of classes, which in this case would just be 2. And I don't know why I didn't recognize that before. Should be good. The new layer within our classifier will automatically have requires grad equaling true, and having created a new final layer to replace the old one, such that the number of inputs for this layer is equivalent to the number of outputs from the previous layer. There is nothing new here. Now we simply have a final output layer with 2 classes. Now to replace the previous last layer with the new one, this one right here, we simply call model.classifier 6, and we set it equal to the last layer, replacing this layer at element 6, index 6. So what we can do actually is print the model again, print model, and as you can see, the last output is 2. We've successfully modified the network to suit our purposes by changing the number of outputs for the last layer from 1000 to 2. For concision, one can simply print model.classifier 6.outFeatures, and it would simply reflect an output of 2, which is what's expected. We have successfully modified the model to be trained on our dataset. Now let's begin the training process. Or more accurately, let's begin training only the classifier portion of our model. First and foremost, if GPU is available, we should move the model to GPU with model.toDevice. As training such a large network will still remain a lengthy process, in training this model, we still make use of cross-entropy loss. As for the learning rate, since we are dealing with a much smaller data set, it would be to our advantage to slow down the learning process and put down a lower learning rate. And having already modified the training process earlier, we should be good to train our model. Now, you know what? Before training our model, a couple of things have come to mind. Is that since we are dealing with a relatively small data set, let's just use a smaller number of epochs. That should help. And as far as augmentations go, from previous experience with this dataset, the random rotation transformation will tend to actually hinder the performance. Again, one should always try and experiment with different types of transformations and see which ones better aid in model performance. Aside from that, everything should be fine. We specified a smaller number of epochs. The learning rate is good. All right, so what we can do now is rerun all of our cells. Run all. I will see you guys on the other side. All right, it seems we reached a whopping 84% accuracy in the first epoch, with only a 300-400 image dataset. And we closed in at almost 90% in the final epoch. This would be very hard to achieve without the use of a sophisticated pre-trained model such as AlexNet. In fact, attempting to classify this data by training our neural network from scratch would not be feasible. This is one of those cases where it's easier to harness the power behind already pre-trained sophisticated models that have already been developed for such use cases through rigorous research. More specifically, this was a case where we did not have enough training data to train our own network with. We barely had 400 images. So instead, we relied on another pre-trained model, the AlexNet model, that has already been trained on very similar datasets, which has already learned to extract relevant features that you would want your neural model to extract. And it did just that, with roughly a 90% accuracy. And by looking at our graphs, it also shows minimal signs of overfitting. However, the changes in losses and accuracy are extremely sharp. This is likely due to the relatively small dataset that we are using. A larger dataset would definitely improve the quality of those graphs. Now let's see if our model is good at predicting images from the web. Let's grab an image of an ant from Google and see if our model can predict it. So on Google, google.ca, misspelled that pretty badly. We write ant. And let's grab the following ant. Copy image, address, and right onto here. That's not going to work. Let's try another image. Let's try the following. Copy image address. All right. Running the following cell. Running this one for the appropriate transformations. On second thought. Yep, we're fine. And it predicts an ant. This is really good. Let's try the image of a bee. Let's pick a hard one for our model. How about this one? Probably not that hard, actually. Let's try that one. That one's pretty cool. Copy image address. All right. And it predicts it as a bee. It successfully predicts the images. This is really good to see. Based on a dataset of barely 300-400 training and validation images, we were able to effectively create a model that can generalize itself to new images. Let's now run it on our validation images and see what kind of accuracies we get. All right, as we can see, it predicts most of our images correctly, except for one, a testament to its 90% accuracy, or 88% I should say. As you can see, it's relatively easy to use a pre-trained model when the conditions require you to do so. As promised, however, we're going to try a different pre-trained model, VGG16. So we'll go back up, and rather than AlexNet, which I instantiated somewhere over here, there it is, we will load VGG16. Now, this sophisticated model, VGG16, a fun fact about VGGNet, consisting of 16 convolutional layers, VGGNet is trained on 4 GPUs for 2 to 3 weeks. We will use this pre-trained model and see how well it does on our ants and bees data. So what we're going to do is run after is go to that cell and run after. I will see you guys on the other side of the training process. Alright, having used a much more sophisticated model, we see that it reaches much higher accuracies than AlexNet at a much higher rate. Looking at our graphs, we see that our model overfits at around epoch 7, and since we were able to reach really high accuracies early on, running 10 epochs probably doesn't seem so necessary, so we're going to reduce the number of epochs to 5 and retrain the model. Notice how this training process took a lot longer, as VGG is much more sophisticated in its architecture, with much more convolutional layers. Alright, let's go back to instantiating it, and restarting the training process. I will see you guys very soon. So we were able to reach a 92% accuracy at the final 5th epoch, and there seems to be minimal signs of overfitting, no signs of overfitting actually. Let's test a few images from Google again. You know what? Instead of grabbing new ones, let's just stick to these ones, see if it predicts it correctly, which it probably will. It will predict this is a bee, I'm sure. Let's grab one of an ant. Ant. Let's grab this ant over here. That seems like a very strange ant, rather. Let's try that. Hope it gets it correct. And indeed it does. We test this on the validation data again, and it gets most of them right once again, except for one. We can see that this model is also highly effective at predicting most of the validation images, and to be quite frank, this does not look like an ant in the least, but aside from that, our model is very effective at predicting most of the validation images, and it was able to perform so well, having only been trained on a dataset of roughly 300 images. This is really impressive, and that is all we will cover for transfer learning. I hope you are now able to see the benefits behind transfer learning. It is extremely useful when one doesn't have enough labeled training data to train their model on from scratch. In even other cases, harnessing the weights behind already pre-trained models that have already shown very good performance on similar tasks can save a lot of time and return really good results. In the next section, we use transfer learning to build a highly sophisticated project which entails recomposing images in the style of other images, our most advanced project in this course, namely style transfer. I will see you guys in there.